Today we're going to be talking about exploring the solar system, and I've titled this Exploring the Cosmic Landscape. And really what it is, it's sort of a stepping out into the solar system that we're doing in modern times. So now I've sort of dropped the historical perspective from going back to ancient times and talking about sort of where we are now in mapping out the solar system and really understanding what these things are that are orbiting about the sun. And I'm going to use that as kind of a jumping off point to what we're going to be doing the rest of this course, which is leaving the solar system far behind and traveling out into the galaxy, looking at other stars, and then eventually other galaxies and the universe itself. So, does anyone know where this is? What does this look like? Mars, good, wow. That's great. I was hoping someone would say the desert or something. The thing that I wanted you to see, though, in this sort of picture of the landscape of Mars is that it's both foreign and familiar. You know, there's something about this that you look at this and you're like, yeah, you know, it's not that different than things I've seen here on Earth. But in other ways, it is. And in the sense that it really is desert-like, more desert-like than any desert on Earth, in the sense that it's really, really dry. We know that Mars is effectively, there's no liquid water whatsoever. And so in that sense, it's very much like a desert. It also has an extremely thin atmosphere, so that it's something of a harsh environment with wild temperature swings from night and day. Again, a lot like the deserts here on Earth, but even more so. The fact that we have such amazing high definition images from the surface of another world is something that I hope you don't take for granted. I mean, this is an amazing thing, that we've now mapped out the surface of Mars to a degree that's probably better than maps we had of the surface of the Earth 50 years ago. So it's really a testament to what we've been able to do, putting probes into space on this really distant body, landing them at times and being able to take images like this. It's really an incredible thing. So in that sense, you know, we are living in the space age. I mean, it's not quite the thing where we're all wearing jetpacks and we get to go to these planets regularly. But at least robotically, we are exploring the solar system, and we have within our capabilities to send missions to other planets, other moons, and really map out the solar system with a lot of detail. So far we've landed people on the moon and returned rocks. You know that. But we have robotic landers. We put them on the moon, Venus, Mars, Titan. Titan is one of the moons of Jupiter. Saturn, sorry. We've put robotic landers on an asteroid, and recently we've landed on a comet. So we've done all of these things. We've sent probes into the atmospheres of Venus, Mars, Jupiter, and Titan. We've flown spacecraft very close by all the known planets, and we're fastly approaching Pluto. We'll be at Pluto in about 6 months, and you'll probably see news. If you're interested in that, keep your eye open for that. I'll talk about that in a little bit. We've done radar maps of some of the planets, and there's an extensive exploration of Mars in progress, and we've done, these last two things are things I'm actually going to focus on in this lecture, that these ongoing explorations of the planet Mars, and also some things we've learned about Jupiter and its moons that are pretty fascinating. So what I've decided to do is, with this lecture, I just wanted to give you a taste of the kinds of things that we're doing to map out and learn about things in the solar system. This certainly isn't exhaustive, and you could have an entire course on the solar system and what we're learning about those, you know, those planets and other bodies in the solar system. So today is just sort of like a cook's tour of some cool things that I cherry-picked out of what we know about the solar system. And again, we're going to use that as a jumping off point to go to the stars. So we're going to be focusing on Mars and Jupiter's moons for most of this lecture. So Mars has always fascinated us. Okay, Mars has been a source of fascination for a long time, moving into the era where people were beginning to understand what Mars was with more detailed astrophysical studies. So for example, it's been known for quite a long time that that Mars has an orbital period of about 2 years. So in that sense, it's very similar to Earth. Another thing that you'll notice in this picture is this is a picture of Mars. It has ice caps. So just like the Earth, the poles have these ice caps. It's the same thing on Mars. So in that sense, it sort of looks like the Earth. It looks like a mini Earth. It's smaller than the Earth. The other thing is it's got an axial tilt that's also very similar to our own axial tilt. So that means it goes through seasons. There's a Martian summer, there's Martian winters in the northern and southern hemisphere. And so again, it's a lot like the Earth, so they have similar seasons. Even its rotational period is about a day. It's a little bit longer than a day, but its rotational period is about a day and 40 minutes. So if you were on Mars, you would experience the day-night cycle in a way that's not that much different than we experience here. And it doesn't have to be that way. But there are other ways where Mars is actually a lot different than the Earth. And it has to do with both the fact that it's a little farther away from the sun and that it's a lot smaller. It turns out that something really important in the difference between Earth and Mars is in our magnetic fields. So the Earth has a magnetic field. And that's why you can hold a compass and know which way is north. Okay, a compass needle will point north because of our magnetic field. Mars, on the other hand, basically has no global magnetic field. And you may ask yourself, well, why do I care about that? I mean, fine, so you can't use a compass on Mars, who cares? It turns out that matters, though, and it matters for maybe a subtle thing that you haven't thought very much about, but the sun, it turns out, is spinning out all kinds of high-energy charged particles. And that is called the solar wind. So there's all kinds of charged particles coming from the sun, and they're raining onto the planets. Now, the Earth has a magnetic field, and it turns out that this magnetic field deflects those charged particles. When they come along, they get deflected off this magnetic field. And sometimes they actually get deflected in such a way that they're channeled along the magnetic field and rained down into the poles. Has anyone ever seen the Northern Lights or heard of the Northern Lights? Oh, have you seen them? Cool. Where were you? In Finland. Okay, so you have to be very far north. It must have been in the wintertime when it's dark a lot of the time. If you go very far north on our globe, and especially in the wintertime, you can see the Northern Lights at night, and it's just this amazing thing. And people raise their hand that they've heard of them. They're really a beautiful thing. And what they are is they're charged particles that are raining down into the atmosphere, that are then hitting things in the atmosphere and glowing these cool colors. But that's because of the magnetic fields where those charged particles get channeled in along the poles. So if you're up towards the pole, you can see them. But for our purposes, one thing that our magnetic field does is it protects our atmosphere. If that magnetic field wasn't there, those charged particles would just rain in directly on our atmosphere, and over time, they would start stripping off our atmosphere. Now, our atmosphere is important for us for a lot of different reasons, but one of the things it does is it actually heats us a little bit. It acts like a blanket. Have you heard of the greenhouse effect? Who's heard of the greenhouse effect? That comes from the atmosphere. So there's molecules in the atmosphere that keep the Earth a little bit warmer than it would be otherwise, about 30 degrees warmer than it would be otherwise. So if you got rid of our atmosphere, it would get very cold on Earth. In fact, if you got rid of our atmosphere, you couldn't have liquid water anyway, because if the air pressure is very, very low, water will not stay liquid. It just can't happen. It would act more like dry ice does. So the fact that we have an atmosphere is very important for both keeping us warm and allowing us to have liquid water on the surface. But Mars has a very, very thin atmosphere, almost certainly because, or at least contributed to the fact that there's no magnetic field on Mars. And its atmosphere is only 0.7% of the Earth's in terms of atmospheric pressure. So it's very, very thin, wispy atmosphere. So there's no greenhouse effect. And so not only is Mars farther away from the sun, which keeps it colder, it has no atmosphere to act like a blanket, so it gets even colder. So you have a very cold surface temperature of Mars. It's about minus 50 degrees Celsius, minus 58 degrees Fahrenheit on average. So it's very cold, very, very cold. And of course, no liquid water. And we think liquid water is fundamentally important for life, and so the fact that there's no liquid water on Mars makes it a pretty inhospitable place right now. So today, Mars is really a very harsh desert. There's all this talk about going to Mars, and people want to, and it would be very amazing if we could send people to visit Mars. But I wouldn't be the first person to say, I'm going to go live my life out on Mars, because it's a pretty harsh place. It's very cold, there's no atmosphere, there's nothing alive there. I mean, it's a pretty harsh environment. If life does somehow exist on Mars, it doesn't live on the surface. We think that's pretty clear. It's possible that there is life somehow underground on Mars. We don't know that yet. And if it is life, it's probably, microbial life, right? It's not like creatures, almost certainly. However, people are asking themselves, what about Mars in the past? Okay, because, if you think about this atmosphere that's being blown away by the solar wind, that means that maybe if you go back in time far enough, before the solar wind had time to blow the atmosphere off, maybe there was a thick atmosphere. So maybe there was liquid water in the past on Mars. Maybe there was life in the past on Mars. And that's one of the motivating factors that's caused people to explore Mars so much. In fact, this is just the NASA landing sites where we've actually landed probes and robots on the surface of Mars. This is the Martian globe. Here's the poles where there's ice packs. The first landers were the Viking landers in the mid-1970s. And actually, there's a couple of rovers that have landed in this century, Spirit and Opportunity rovers. And in fact, the Opportunity rover is still going. So it's still chugging along, going along, studying Mars. Now, the most recent thing that we've landed on Mars is this thing called the Curiosity rover, and that's what I want to talk a bit about. It landed on Mars in 2012, and it is still going. It's about the size of a small car. It's robotically controlled, and it's roving around Mars, doing experiments and trying to figure out whether perhaps conditions were right on Mars in the past for it to be habitable. This is a movie that animates how this landing occurred for the Curiosity rover, and it's really just an amazing feat of engineering. I mean, this is not a real landing, this is just a movie mock-up of what happened, but I've actually provided a link here of real footage from the spacecraft itself when it landed on Mars. But this gives you sort of a better overview of what happened. There was this probe that was coming into the atmosphere and first of all just breaking because of friction onto the thin Martian atmosphere. But because the Martian atmosphere is so thin, it's hard to slow itself down, and you don't want to just let this thing slam into the ground. It'll break, and it's $1 billion thing. You don't want to break it. So first of all, they had this parachute open up, but then the rover's in there. So watch what happens. So it's got this jet that's amazing. So it actually did that. It came off, parachute, this thing came out, and then it slowly set itself down on the surface of Mars this way. And if you watch this thing here, if you go to this link, you'll see live camera footage from this thing really was coming in, and it hits the ground. You can see like a rock shoot up when it hits the ground and stuff. So there it is. It lowers down on this cable. So here is an image of Curiosity that it took of itself once it got on the ground.
Selfie.
Yeah, it was a selfie. So it got its little, it had the camera on its arm, and it took a bunch of images of itself, and then beamed it back, put it on Facebook here. So the mission here of this thing, this sort of complicated contraption, it's got laser beams on it, it's got like all kinds of, it's got a chemical laboratory on it, geological tools and stuff. Its mission is to figure out, is the surface of Mars potentially habitable, or in the past was it potentially habitable? That's the question. And by habitable we mean, did it have liquid water, essential elements for life, carbon, nitrogen, oxygen, phosphorus, and sources of energy. And it has lots of equipment to do this stuff. So just to give you a sense, wow, we've got this basically SUV thing riding around on Mars. Here's an image and it's going around at different interesting spots on Mars. And here it turned around and took a picture of its tracks. Notice that Mars is this kind of red, rusty color. It really, in some sense, is rust. The current findings based on Curiosity and other experiments is that it does seem like the surface of Mars had flowing water on it. There's a lot of evidence of ancient riverbeds and stream beds. So there was at one point in time in the past water flowing on the surface of Mars. And that water, by the way, was non-acidic, which is good for life. And also, a lot of the key elements for life were present. So carbon, hydrogen, nitrogen, oxygen, etc. And it doesn't mean for sure that organic molecules existed. This Curiosity is not equipped to find them if they were there, or doesn't have the sensitivity necessarily to find them if they were there. But all indications are that the ingredients for life did exist on the surface of Mars at least sometime in the past. Any questions about that? We also know that today ice water does exist under the surface of Mars. So here's a map of basically the ice content underground in Mars. And so white would be little ice, and purple is a lot of ice. And so there are regions where there's a lot of ice that sort of exists locked up underground on Mars. And so again, this is another, people have this idea, well, maybe there's some life percolating under there. So the upshot of this is that, it's very possible that Mars was once warmer and wetter. And that this is an artist's conception, but you could imagine that, 1 billion or 2 billion years ago, there were vast oceans, liquid oceans, on the surface of Mars. And so what we'd like to do is go and spend a little bit more time on Mars and see if there's any evidence that maybe there was life living in these oceans. And if so, that would be profound, right? Because it would mean not only did life emerge on this one planet around our star, but it also emerged on this other planet around our star, which by extension means maybe it's not that uncommon for life to emerge. Questions about that? Okay. So we're going to fly by here and talk about something else. We're going to step out into the solar system to Jupiter. Now, Jupiter is a planet that we've done a lot of flybys of. We've sent spacecraft whizzing by Jupiter a couple times. But there's this probe called Galileo, named after Galileo Galilei, who discovered the 4 big moons of Jupiter, that went and actually was in orbit around Jupiter from 1995 to 2003. And so what it was doing, it was on these kind of looping orbits around Jupiter that would plunge it into Jupiter's atmosphere. It could study the atmosphere of Jupiter. But then the orbits would come out far enough that it would do these close flybys to Jupiter's moons. And so we could take these just amazing pictures of Jupiter's moons that are just, really spellbinding when you see them. In particular, Galileo studied all of these moons, but in particular, I'm going to talk about one of them called Europa. So it turns out that Galileo found evidence, pretty strong evidence, that lurking beneath the surface of Europa is an ocean of liquid water. And in fact, that result was considered so important that the orbit of Galileo was hard enough to control. They were worried that Galileo was going to slam into Europa and therefore contaminate it, because we want to go back and with a more pristine mission later. So instead, in 2003, they decided to direct Galileo to just crash into Jupiter. So they directed itself to just destroy itself by going into Jupiter and burning up. And so that's why it's not there anymore. It basically killed itself in 2003. This is an image of the surface of Europa, which, by the way, is just incredible that you can see a picture like this of a moon orbiting something that far away. This is the moon of Jupiter in this incredible detail. Now, what are we looking at here? It turns out that there's all these sort of crisscrossing patterns all over the surface of Europa. And what we see is that the surface of this planet is basically ice. But these cracks reveal that there's some shifting going on underneath that ice that are leading to these cracks. The other thing that we notice is there are very, very few impact craters on the surface of this moon. Now, if you look at our moon, right, the thing that sort of stands out about our moon is just covered with craters, right? Our moon just got craters all over it. Because it's being pelted over time for the last, several billion years, it's been being hit by meteors and stuff that create these craters. Here, there are very, very few craters. And it's not like the rate of bombardment is that much smaller out there near Jupiter. So what we think is going on is there were these past impacts, but then they got smoothed over. That is, the surface is being repaved because we think underneath it is this liquid water. So stuff will slam in, it'll create a crater, but pretty soon water will get churned up and just pave over it and refreeze. So its surface is constantly being smoothed over, and that's why you don't see this long record of cratering on the surface of this thing. Here's an image, a close-up image of the surface of Europa. This is 25 miles across, and we're looking at these cracks, okay? It's fractured ice, and the thing that's kind of amazing about it is if you do a flyover of the Arctic oceans on Earth, you will see this same kind of cracking on the ice sheets that float on top of those oceans. So it looks very, very similar to the kind of oceans we have underneath ice packs on Earth. And the physics of it wouldn't be that much different. And so that's another piece of evidence that underneath this ice is some kind of liquid water that's churning and shifting. Are there questions about this? Yeah?
Isn't it too far away from the sun to have liquid water?
Great question. That is a great question. Yeah, so the question was, isn't this too far away from the sun to have this liquid water? That's a great question. I'll come back to that in a second. I'm going to address it. Because you're right, naively, yeah, it's cold out there. How the heck is there possibly liquid water underneath this ice sheet? However, there's evidence that it's there. So how, it's sort of a conundrum. So the evidence that I just talked about is that there are all these cracks and features that make it look like there's liquid water there. Another thing that's a little bit more subtle, but it's really interesting, the Galileo spacecraft also discovered that there was a magnetic field around this moon. And how do you get a magnetic field? The reason why the Earth has a magnetic field, by the way, is because it has a hot molten core that's basically made of metal, and it's churning and moving. And so if you have charged particles that are moving around, that's how you create magnetic fields. The reason why Mars doesn't have a magnetic field is because its core has cooled down and it's not churning anymore and moving like that, and its magnetic field ran out. It doesn't exist anymore. So one way to make a magnetic field on Europa is if you have a salty sea with water that's sloshing around with charged particles in it, that will generate a magnetic field. And so because they measured the existence of this magnetic field, it's another piece of evidence that some kind of salty water, perhaps, churning around underneath the surface of this moon. Now, as we just heard, this is weird because Europa and Jupiter are really far away from the sun, right? Mars is really cold, and it's much closer to the sun than Jupiter. Here we are at Jupiter, we're 5.5 AU, 5 times farther away from the sun than the Earth is. And yet, we find this thing that's supposed to have liquid water. How is that possible? Well, it turns out that Europa has another source of energy besides the sun. Something else they can get energy from to extract heat that's not the sun. And that is Jupiter itself. It turns out that Europa is orbiting close enough to Jupiter, and it's on a little bit of a, its orbit is a little bit funny. It plunges a little closer to Jupiter sometimes than others. And just like the tidal forces between the moon and the Earth make our tides rise and fall, the strong tidal forces from Jupiter kind of squeeze Europa and pump energy into it by squeezing it. Is that working? Let's see. Play that again. So as it orbits around, it's getting squeezed by the tidal forces. And imagine you had a snowball or something, right, that was frozen. But if you just kept squeezing it and pulling on it, you can imagine melting that ice just by sort of, squeezing it and pushing on it, adding energy to it. That's basically what's going on here. Jupiter is squeezing it and pumping energy into it and keeping that ice just below the surface, turning it into liquid. Does that make sense? Are there questions about that? Yeah.
So, does it mean that the surface size is constantly changing?
A little bit. So it's not, drastic, but it is a little bit changing. And we think that's one of the causes of all these fractures, that it's constantly being kind of squeezed. You imagine if you had like a ball of ice with liquid underneath and you squeeze it a little bit, it would crack. And so that's kind of where we think these cracks, all those cracks that we're seeing are coming from. So what we think is going on then is that there are these very thick ice sheets, and then underneath these ice sheets are these oceans. And in fact, it's possible that every now and then there's sort of cracks up through the ice that then can spout up water up through the surface. Now, one of the things that could very well be going on, right, is there could be life in these oceans. We know that there are organic elements here. I mean, organic molecules. We believe there are organic molecules in these waters. We don't know that for sure, but we think there might be. And if so, you could imagine life somehow emerging down here in this vast under ice ocean. And there are efforts ongoing today on Earth to look for life in the deepest Arctic waters that we can find to see if you ever see life on Earth in those conditions. As far as we can tell on Earth, whenever you have liquid water, you have life. And so this object, Europa, even though it seems like a weird candidate, is actually one of the most interesting places in the solar system to look for life right now. And there are ideas in the works. I mean, there are initial ideas in the works to bring some kind of lander to get here and sample water that might be coming out, for example. But there are sort of really ambitious ideas of effectively sending something down that would drill through the ice and then have a submarine that could sort of swim around and explore this ocean on this other world, in much the same way that the rovers are driving around on the surface of Mars. It's not beyond the realm of possibility that we could do something like that. It's interesting to think about, but there's very likely more water on Europa than there is on the Earth. Because the Earth, right, you hear this thing all the time that 75% of our planet is water. 75% of the surface of our planet is water. Right? Most of our planet is not water. We're not made of water. Right? It's just, it's just in the oceans. And compared to the size of our planet, the oceans even aren't that deep. So if you take all the water on Earth, it would be sort of this size, and all the water in Europa could be this big. So in terms of absolute volume, there might be more oceans on Europa than on Earth. And imagine what's there. Imagine what could be in those oceans. Questions about anything? Okay. So what else are we doing? What other exciting things are going on? So in July of 2015, a new spacecraft is going to have closest approach to Pluto. So there's a spacecraft that's called New Horizons. And New Horizons is a NASA mission, and actually this is an image of Pluto and its moon Charon that was taken by this probe as it's now starting to get close to Pluto. And the intention is to go study Pluto in great detail. It took 10 years for this probe to get out there, which is actually pretty fast. You can actually go on the website of New Horizons and track where it is. So right before lecture, I went and got this picture. See the dates here. So this is the Earth. This is the orbit of Jupiter, Saturn, Uranus, Neptune, and then here's Pluto. And they've hooked this thing up right so that Pluto is at its orbit, and they figured out the trajectory in such a way that it's gonna, they're both gonna hit each, they're gonna fly right by each other, right? So it's not just the trick of getting out to the distance of Pluto, but you also have to time it so that its orbit lines up in the right way. And you see it's getting very, very close. So currently, it's about 32 astronomical units away from the Earth, and it's about 1 astronomical unit away from Pluto. So in the scheme of things, it's getting very, very close. And it took, like I said, 10 years to get there. And there are a lot of questions about why are we doing this? These outer bodies like Pluto, and there's stuff that's even farther out there, rocks that we think are even farther out there. Things like this are left over from the very formation of the solar system itself. And so by studying these rocks, these things like Pluto, the dwarf planets that are out there, we hope to get a better sense of what the solar system was like when it first formed, why it formed that way, what kind of stuff is it made of, etc. Okay. So boy, that thing is pretty far out there. We're almost at Pluto. You might ask, well, how far have we sent things? And this diagram gives you a sense of the farthest, the most distant systems that we've sent out. So these are the most distant probes the humans have sent into space. It's hard to read here, but this one's called Voyager 1, Voyager 2, and then these are the 2 Pioneer probes that were launched. The New Horizons, on this scale, it's sort of hard to see, but here's the orbit of Pluto. And so New Horizons is almost at Pluto right now. So it's sort of a distant 5th in terms of the most distant things we've sent out there. However, Voyager, which is the most distant thing, it was actually launched in 1977. So it's taken this thing about 40, almost getting on 40 years to climb out a distance which is about 120 astronomical units away. So, it's taken it 40 years to get here. So it's now well beyond the sort of orbit of Pluto, and it's venturing into sort of an area that is roughly defined as the edge of our solar system, but it depends on how you really define the edge. Different people have different definitions for what the edge of the solar system is, but it's certainly well beyond the orbit of Pluto. And so when most of us think about what the solar system is, most of us are thinking, well, where are all the planets? And, the planets are in here, and it's beyond where the planets are. That's for sure. Yeah.
When they get out the solar system and there is no solar energy, how do they move around?
So that's a great question. So they don't do much. So the question is, how do they move around and do things when they're so far from the sun? Because if you're so far from the sun, you can't use solar panels. So they have fuel cells. Some of them have basically nuclear powered fuel cells in them to power them. So they're actually not relying on solar panels. But these systems here, like Voyager, it's not really doing that much anymore. It's sending back very, very weak signals. It's got some information. It's still doing some science. But it's not flying. It's basically just coasting now. So basically it got kicked up by doing flybys of planets and other things and started going fast. And now it's moving pretty fast. I mean, it's moving 17 kilometers a second, but it's just headed out. And it's not really headed anywhere in particular. I mean, it's just going. And so it's not actually using very much energy at all right now because it's not doing very much, but sending back very weak radio signals to us. But that is an issue. How do you power these things when they're so far away from the sun? So that's where we are, okay, in terms of solar system exploration. And you might ask, well, okay, Voyager's headed out there. Like, what's it going to find? Like, what's next for Voyager? Is it going to run into the next star, and we're going to start to be able to see the next stars and study that solar system maybe that's there? Well, unfortunately, it's a little harder than that. So here I've made a really simple diagram. Here's the sun. And imagine we're looking at Voyager there, 120 astronomical units away. And let's take that distance, let's take that imaginary circle for the orbit or the distance of Voyager, and shrink it down to the size of a dinner plate. Okay? How far away is the nearest star? It turns out on that scale, the nearest star is about half a mile away. So from here, if we put our dinner plate down, it's basically an In-N-Out burger. That's the nearest star. So that's a long way. And it took Voyager 40 years to get to where it is now, to get to the dinner plate. So it would take Voyager a long time to get to an In-N-Out burger, right? And unfortunately, Voyager isn't even headed next to the nearest star. It's headed off in some random direction. So it's going to be a very, very, very long time. In fact, Voyager may never cross into the orbit of another star and be bound to another star. It might be, but it would be really long from now. To get a sense of this, another way of getting a sense of this is if you took the sun and you shrunk it down to the size of a golf ball, the nearest star to us is called Proxima Centauri. It's actually smaller than the sun. It would be about the size of a marble, but it would be 2,500 kilometers away, it'd be in Florida. That's what we're talking about. So if you're talking about traveling to the stars, okay, if you want to get in a spaceship and go to the stars, that's a hard thing to do. That's a very, very hard thing to do. In fact, if you were traveling at the speed of Voyager, it's about as fast as we could launch something, it'd take about 100,000 years for us to get to the nearest star. Now, it's not beyond the realm of possibility to conceive of such a mission, right? You can imagine building an ark, right? And like, you're just going to live in that ark, and you're going to die on that ark, and your children are going to live and die on that ark, and you're going to go 100,000 years, and you're going to get there. But that's what it would take. Unless you have some much, much faster form of travel. So what's the landscape like beyond this nearby? This is our nearest star too. Like, this is the nearest star. That's 4 light years. Here are all the stars within 35 light years of the sun. Here's the sun. Here's Alpha Centauri. This is our nearby star system here. Proxima Centauri, Alpha Centauri, there are a few stars that are all bound to each other. They're all orbiting around each other. They're here. But then, you step out, there's all these other things. There's some big, bright blue ones. There's Sirius. That's one you may have seen in the sky. That's 35 light years. This is 65 light years. It just keeps going, right? This is 250 light years. Keeps going. Yes?
Are those like actual stars that exist, or just like scientists predict their?
These are actual stars that exist. That we know where they are. We've seen them. We know how far away they are. We know how bright they are. We know what their masses are. We know this. This is a map, like a real map. And, over the next few weeks, I'll talk to you about how we know all that stuff. But you might be asking yourself, wait a second, how do you know all that stuff, right? You just told me that you can't go there. Like, how do you know this? I mean, you showed me these pictures of Europa, which are awesome, but you sent a spaceship there. How do you know this, right? That's kind of going to be what we're going to do for the next week or so. We're going to start figuring out how it is that we can know so much about this vast universe that we have no chance any time in the near future of ever actually going and visiting, right? I mean, for example, we know a lot about the sun, a lot about the sun. No one has ever been to the sun, you know. We don't go to the sun. But we know a lot about the sun. How? How do we know so much about these places that we haven't been? So that's sort of the, you know, this is sort of what I wanted to end with here, right? The stars, unfortunately, for us, are just too far away for us to visit directly with spaceships. Certainly right now, and probably for the next 1,000 years. I mean, certainly for the next couple hundred years. You can imagine a robotic mission, maybe, but you'd have to be very patient to do it. So for celestial objects that are well beyond the solar system, the only way we can learn about them is to study them with telescopes. And what does that mean? That means you just sit here and wait for a light from those objects that has either been reflected or shining to come and hit you, to hit your telescope, and then you have to interpret that light. Okay? So effectively, how we have learned about the universe is by collecting this light and squeezing information out of it. And it turns out that light has a tremendous amount of information in it. You might not think of it very much, right? But there are some things that you do have experience with information from light. Like, for example, you know what color my shirt is, right? And that's because my shirt is reflecting purple light. So your eyes see that purple. What they're really doing is effectively interpreting a wavelength. Okay? The purple light has a different wavelength than the blue light. And it has a different wavelength than this green light that's making this laser pointer. And so your eyes are squeezing information out of light by interpreting color. But it turns out that with modern instruments called spectrographs and with telescopes, we can squeeze even more information than that out of light. And you can learn what things are made of. You can learn how fast things are moving. You can learn a tremendous amount about the makeup of the universe and how it was convolved. And finally, because light moves at a finite speed, okay, it travels at 186,000 miles a second. So by looking at things that are far away, you're seeing the universe as it was in the past. And so by looking at things that are progressively farther and farther and farther away, you can build basically a movie, like a timeline of how the universe was in the past and how it is now, and string together pictures that way. Okay? So that's what we'll be doing next week. Have a good weekend.